Classical Physics Tutoring Chapter 4 Section 4 Thermal Process. This is Thermodynamics, Classical Thermodynamics. Okay, so in Classical Thermodynamics, what you do is to look at the things like this is a system, right? And you add dq, the heat energy. So what's happened to this system? The system described by pressure and volume. Then internal energy U. Okay, so what happened is when you have ideal gas and has a weight here, and the purpose of weight is to keep pressure constant, and you have a volume, so you have some internal energy U, right? And you bring in heater and give heat energy. So what's happened is, probably since pressure is constant, volume increase, right? So this is a thermal process. You have to understand the exact meaning of du equals dq minus p v dp. Now in this case, p is constant, so it's going to be delta u, internal energy increase is going to be delta q, the heat energy given, minus p delta v. And what's minus delta v? In the ideal gas, you expand this much, so delta v is considered the kinetic energy spent. So from delta q, the heat energy minus energy spent is going to be the increase in internal energy. Then what is internal energy? Well, the gas, if it's not ideal, it's not all about pressure and volt, right? Do you remember van der Waals? There's other force inside. So it's a little bit more complicated than PV equals const. Okay, so the internal energy, we assume internal energy exists other than the kinetic energy and heat energy. Okay, so that's what this equation is about. So du is heat energy given minus work performed is going to be internal energy. So internal energy in the ideal gas is pressure, volume, and temperature. Well, even not ideal gas, the three parameters. So du is actually T plus du dv. So why we don't have a dp? There's no p here. The reason is when there's no internal energy depend on T and V, but P is a function of V in the ideal gas. So this is just it's not independent variable. Independent variable can be only 2. Okay, so put that into this equation, we get dq, heat energy, is plus dv. Okay, so the heat energy change is the internal energy change over temperature plus internal energy change and pressure change over volume. Okay, now this is the basic equation to explain all the thermal process. we introduced several thermal process, but it's based on this equation. When you fix the one parameter constant, and for example temperature or pressure or volume, whatever, then you name a different thermal process names, and it's all why such a names given to certain process. It's all historic, but this is basically the basic equation. If you know this equation, then classical thermodynamics is done. You're done with it. But you have to know the meaning of each. So if it's not ideal gas, for example water, then what's happened? Okay? Or it's metal piece, then what's happened? Well, if you understand this equation, you can answer all of this question. The first one, the special name is given, is adiabatic process. This one is isolated thermal system, means there's no DQ, no heat energy exchange from outside. Within a system, net heat energy is 0. Okay, so in this case, the du in the ideal gas is the du depend on the temperature. If you bring this equation back, this one is 0 and this part is du, right? So the du plus p dv equals 0. Okay, so what's happened is the when you take integral, u should be p dv in the c, and this u depend on the temperature, right? So the u is the ideal gas. When we can establish the general equation, is called let's look at this side. dq is 0, so this for ideal gas is uct. So the actually the c delta t plus delta pv is delta q, which is 0, right? The u equals delta u equals c delta t equals delta pv. Why we can claim this? Because ideal gas internal energy increase is either temperature or equivalent term is delta pv, kinetic energy. This pv is kinetic energy and translation is temperature in the ideal gas. If not ideal gas, it's not necessarily true. You have to deal with that equation. So what's happened is, if there's no increase, okay, the delta u is 0, no increase. Integral, you take the ct plus pv equals const. Ideal gas is temperature is 0, then volume shrink to 0, c is 0. That means ideal gas ct plus pv is 0. They are proportional. So that's why we have a Avogadro's equation here. PV is proportional to T1, T2, and constant K here. Okay, and this one means thermally isolated process. There's no delta Q coming. Internal energy is just the internal molecules flying speed, which is the PB or temperature. Okay, and enthalpy. What is enthalpy? Enthalpy defined by internal energy plus PV. And for ideal gas, the pretty much PV is everything, and the internal energy, because the molecule flying speed is the internal energy, nothing else. The molecule vibrating, we don't consider that as a part of internal energy. But when you handle the water or metal, this molecule vibration is the internal energy. So it's different. You have to be able to modify the equations and use it properly for different material. So this is definition of enthalpy. What enthalpy is? The internal energy plus PV. Okay. Then entropy, we went through this. Delta S is C log P2 B2 over P1 B1. Okay. So next one is isothalpic process. Means if we make a temperature constant. So in this equation, the enthalpy becomes 0 because T1 equals T2. You go back to equation here. Enthalpies, the increment becomes 0. Increment 0 means enthalpy is constant. H is constant. Okay. The isentropic process is the reversible adiabatic process occurs at a constant entropy. What does it mean is the adiabatic process is reversible. We're talking about ideal gas. Now we consider the system lose some delta Q in the thermal process. Then what happened is you have this much energy loss. Okay, so isentropic process consider the energy loss, heat loss. Okay, so this is for ideal gas, but not for this process. Enthalpy, you have to add this much energy loss. So obviously entropy also lose this much. So the energy loss is in the process, this process equation modified for the isentropic process. Or later you do some practice problem using actual temperature, gas pressure and stuff, and you calculate numeric calculation, probably give you a very clear idea. Isobaric process, this one's the constant pressure in the thermally isolated process. It's not thermally isolated process. In this case, you give a Q to the system, then the pressure is constant. So earlier I talked about putting a gas in the piston, and volume change this much, but pressure is constant. Okay, in this case the ideal gas still this relationship hold, and enthalpy is going to be the not only temperature has this much volume increase. Well, that comes from the additional heat energy from outside. You heat it up. Okay, so entropy is this equation, the temperature difference. Isochoric process, this one is a constant volume. This one also you give a heat to the process and keep the volume fixed. Internal pressure increase by the additional heat energy. This is a heater. Okay, so, but mechanical work PV is 0, so it's all going to the temperature. So enthalpy is the temperature difference. In this case, temperature climb up really fast because volume is constant. Okay, and the entropy is same equation, the temperature difference. Isothermal process, constant temperature. This process is you keep the temperature fixed after you give delta Q. So what happens is it's expand in such a way the same temperature is kept. Okay, so same ideal gas, this equation hold, enthalpy is 0 because no change in the temperature. The enthalpy is V2 over V1. How much volume increase? This is V1. Okay, now the term steady state process. What does steady state process? Steady state process is when the internal energy doesn't change. That's a steady state. Okay, that means U is constant. And what does this mean is you make other change like volume increase but pressure decrease. Okay, but total energy U is same. You have delta Q, heat coming, but you're losing heat same amount. So internal, for ideal gas, PV is everything, right? Its translation is T. The ideal gas, the internal doesn't increase, but this more general steady state. If not ideal gas or water or solid material, okay, then you get the heat and you lose the heat, internal energy is same, and that's called steady state process. Then internal state change. For example, water's internal state change. Okay, but internal energy is constant. That's a steady state process. So there are many kind of names given to the thermal process because there are many parameters depend on what you're dealing with, ideal gas or non-ideal gas, water or solid, whatever. And you have to fix the parameters like temperature constant, pressure constant, volume constant, and see what's happening. Simplify the equation, and that's what it means. And so we covered enthalpy, entropy, and internal energy, and the heat energy, and the steady state process. So that's all about the classical thermodynamics. I hope you enjoyed this video, and if you like, subscribe.